to you. This is Galactic bringing you another science presentation. We're in the field of astronomy, but currently we're at the other end of the astronomical spectrum, down at the quantum level. We need to understand the building blocks of the universe, but that does not appear at first, at least it did not to me, to be directly concerned with astronomy. That is how I began my course in science. I became interested in astronomical objects, specifically galaxies, and quite specifically interacting galaxies, which I consider to be the most beautiful thing that the human eye has ever seen. It's certainly in one category, since that's the beauty pageant contest. It's hard to compare a spiral galaxy with a beautiful woman, but they do have the same metric, beauty, overwhelming beauty. In the course of my work, when I first started out about 14 years ago in astronomy, in galactic astronomy, I was vastly interested in the interacting galaxies, largely due to the influence of Halton Christian Arp, who was one of the pioneers, along with Fritz Zwicky, in the analysis of interacting galaxies, particularly spiral galaxies. Elliptical galaxies do not seem to interact. That's a very not very often noted fact, but there are a good deal many interacting spiral galaxies. In groups of up to 5 or even 6, it's not uncommon to find 3, but it's like with binary stars, which also there are trinary star systems, and quaternary, I believe is the right pronunciation, 4-star systems such as the trapezium in the Great Nebula of Orion. So this is a little bit of numbers, just numbers. The numbers of galaxies that can interact, the number of stars that can interact, about the same. We could go on, but that's not our subject today. This is the third part of a 3-part lecture series that's run for 3 days. This is the third, where we've been covering the quantum paradox. From a slightly different point of view, although not an iconoclastic point of view, this isn't Samson trying to pull the pillars down on all of us. No, it's not really contrary to anything that's known. Where we're at is where the rest of physics is at in trying to make progress. The nature of the difficulty in quantum mechanics, due to the nature of the paradox, is even difficult to state. It helps to state it in many ways. I believe there are at least 6 major categories of the quantum paradox. It's very easy to name a few. The wave-particle duality. We'll just stop there, and let's enter into our third lecture series, our third lecture in this series about the quantum paradox, with a specific goal. We're attempting to get the building blocks of the universe for a reason. That is, I am. But I do not ever treat myself separately from the rest of science. In other words, what I'm doing, what I'm attempting to find out, to explain to myself as well as to you, is an interpretation of the facts that we have at the fundamental level of science, which can be said, certainly in physics, to have to do with atomic physics. This would be the proton, which we covered in full, and I will be summarizing that as we get ready to go into the deepest water in this field. We're going to get some very elusive answers right now, but we did need to set this up. There is no direct path, even though I may claim to know the path to a better threshold of understanding. It's always a threshold of understanding. Of course, we are attempting to achieve absolute understanding, but my claim is, and I am sure that I can back this up, it's hard to talk about a proof in this case, but the ultimate understanding is personal. that there is no consensual or communal or consortium oriented, just we all agree on what the absolute truth is in any sense. That will never be the case. What is always the case is that science can help in the rational approach to the universe. The universe is rational, and that can be proved. You don't necessarily need to accept that, but I'm kind of showing you where I come from and where I intend to go with you. You're here for a reason, to get some understanding. Not an easy task in the case of quantum mechanics, since it's eluded the greatest minds who have ever lived. However, there is a certain window opening up now, which has not opened up for 70 to 100 years, in the pursuit of understanding which can be shared. That is the definition of science, the understanding that can be shared because it can be proved. There have been very few new insights into the quantum paradox. It's remained a paradox for a century. That's neither good nor bad, it's just the way it is. However, there is a gradient in science. We do have a philosophy of science. Not everyone ascribes to it, but I believe anybody who takes themselves seriously as a scientist believes in the Einsteinian principle. I consider this to be the absolute basis of science, that any question that we can ask of the universe that is a rational question, that would need to be defined, but any rational question we can ask of the universe will answer. It will answer it. Whether we get the right answer or not is ultimately up to us. But you can't fault the universe. There's a trend these days to just say that the universe is playing a trick on us, like it's a projection, or that something is unreal, such as time. It's difficult to justify such statements from one point of view, but it's actually normal from another point of view. Science is always probing. It's pushing the envelope. It's attempting to go where no man has gone before to get new thresholds of understanding. For the longest time, we, as a human race, we're not too sure about the motions of the heavenly bodies above us, such as the sun. If you were to first look at the course of the sun, you have to imagine this, because we all know that it's just an apparent motion of the sun. But if you didn't know that the apparent motion of the sun were caused by the revolution of the earth on its axis, why, you might be tempted to agree with many of the ancients who pointed out that the sun sure does travel fast through the sky. Yes, it seems to, but that's not due to the actual motion of the sun on that path through the sky. It's due to the fact that the earth is turning in the opposite direction than we see. And that's very interesting. I find that fascinating. It's a very simple example that we're all taught in school, but the quantum paradox is very similar. I know the answer to the quantum paradox, but I can tell you that sounds presumptuous even to me. Because, well, for one thing, why would I be so blessed with an insight that not even Einstein or Bohr or Feynman, just to name some names, nobody's been able to figure out the quantum paradox. It has remained, irritatingly in some sense, a complete paradox, absolute mystery, a totally baffling phenomenon, cannot be understood. Feynman said that. He said that no one will ever understand the quantum paradox. I've already proved Feynman wrong, but what I need to do as a scientist is to share that, because if it's not shared, it's not science. It almost sounds megalomaniac, and I do have to be cautious because it's thrilling to know the actual answers. However, what I'd like to say, just to get off the subject of science is not about I or even he. We're not interested in Einstein, although we may be as humans. I certainly am. I think he's a fascinating man. I also am interested, like most scientists, in the lives of the mathematicians and physicists and discoverers, because you learn a lot. But it's not science, it's something else. What we want is what they discovered. Also, what is really precious are the proofs. Now, in mathematics, that can be grueling. I'm not talking about mathematics here. I'm actually not a mathematics major. I've been tested. I'm like in the 82nd percentile, which is relatively high, but it's not nearly high enough to qualify for the field of mathematics in present-day science. So I'm not a mathematician by any definition. However, I have been forced to get into the mathematical basis of how we do measurements, how we use numbers, how we compute, how we use algebra, how Einstein formulated his field equation for gravity, which is now called spacetime. We're going to be covering all of that, but from the ground up. In the last lecture, we extended our definition of the proton and the electron, so we now have a new geometric viewpoint, which is not new. It's actually 250 years old. And it's all the more remarkable to me that Bošković, the man of whom I'm speaking, had a particle interaction theory complete with an algebraic curve for the interaction of two particles before any particles had ever been discovered, long before the electron, long before the proton, which was somewhat after the discovery of the electron. But he lived in the 18th century, whereas the discoveries made in electrodynamics were in the 19th century, and the proton was not discovered until the 20th century. Now, the photon has been known of in some sense since the time of Newton, who, with his corpuscular theory of light, basically established the particle nature of light, which has never been refuted. In fact, it is generally agreed that Einstein offered magnificent proof that the photon, that is, the particle of light, is a real thing. He discovered that in something called the photoelectric effect, which I'm sure you're aware of, but if for any reason you're not, you can easily find out. The photoelectric effect, that's what he got a Nobel Prize for. He didn't get a Nobel Prize for either of his formulations of relativism, relativistic space-time. So we're going to get into that, but where we're at is I'm trying to get back to astronomy. And the reason I got sidetracked, which is not a sidetrack, as I now know, the information that we get in astronomy comes from two sources, essentially. I'm not talking about the solar system here, but extragalactic, what's deep space science. How we understand the universe, and when we say universe, not just cosmology, which is the science of addressing the entire thing, if that can be done, well, it's been attempted. But really, when we're talking about deep space astronomy, it's not about the Big Bang, it's not about the CMBR. Although all of these things are part of the overall picture, science probes everywhere. We don't leave any stone unturned, so to speak. But we're really talking about macroscale objects. Of course, the one that we're most familiar with is a typical planet, although you could say it's not very typical, the Earth. And then there are satellites of planets, and that's about it. There's nothing smaller than that that's spherical. Generally speaking, that can be said. Satellites of planets are spherical. This is a generalization, but I think you understand. This is common knowledge. Planets are spherical. Stars are spherical. And the star is the first luminous object. Everything else is dark matter. It's one way, although that's not how the theory of dark matter was devised. It wasn't, just planets or, asteroids and comets and things that don't glow, things that are not on fire. That's not what is meant by dark matter. We'll return to that later. there is an excellent way of going about getting the correct definition of dark matter, but I'm making a joke. Although you could say, I mean, planets are not stars, so they're not luminous objects. Now, when you go into classifying the structures in macrospace, going to the edge as far as we have seen, which now would be as far as essentially the James Webb Telescope is seen, but really we've seen quite a bit. We can see really to the 10 billion light year radius. That's quite a long ways. Well, what have we found? Well, first we found stars. We've known about them for thousands of years, but we didn't know about galaxies, which is the next largest luminous object. It's not like the galaxy is on fire, but the stars are on fire, and galaxies are made of stars. But they don't look spherical. They look either spiral, and we're most familiar, I think, certainly I am very familiar with the spiral galaxy. Well, that's only 45% of those. There are smaller galaxies going down to dwarf galaxies, something that's been probed. How small can something be before it's not a galaxy? We're talking about in broad strokes here. There's a lot of footnotes when you try to cover a lot of ground in science. You're going to have to leave a trail of footnotes because you really don't want to leave anything out, but time forbids going into every single footnote. So, broadly speaking, 45% of all galaxies are spiral, and there's only one other kind, elliptical. Now, they're called elliptical for historical reasons. They're spherical. They're spherical galaxies, and they're not nearly as exciting. Actually, they are, but you have to look into it a little further to find out what could possibly be as exciting about an elliptical galaxy, which is just a blob, as compared with a spiral. That's gorgeous. Plus, the spiral galaxies typically are made of blue-white stars. That is, they show up as blue-white phenomena. Gorgeous, beyond belief, to me. And I'm not alone. A lot of men find these. And when I say men, I always mean men and women. The elliptical galaxies tend to be composed of red stars. They're older, generally larger stars, and so elliptical galaxies are not only not spiral, they're not diamond-like. They're just kind of rusty. It's like the different. So they're not as exciting. They're not as glamorous. They're not as sexy, Actually, if you look into it further, you'll find out the elliptical galaxies manifest an amazing phenomenon. And I'm not going to go into that right now because we're on a different course. But I'm bringing this into perspective that the reason we're in quantum mechanics, and this is assuming now that you're journeying with me, that is why I produce. I assume that you're going to be interested. If you're not already interested in this course of progress, I expect that you will be. That is my intention, is to get you excited, or if you are excited, to give you the answers you want. To understand these things that we think are just absolutely knock you dead gorgeous. Well, that's, for me, is galaxies. It's not really the proton and electron or photon. But here's the deal. When you study astronomy, and you may already know this, but I'm just saying this to put it out on the table, you realize that you're getting all of your information from light. So light becomes a major commodity. And it's not just that it shows us the galaxy and its colors and its shape. It's that you can read that light. It has a fingerprint. It's unbelievably filled with information. And spectroscopy covers that. Another topic for another time, but light is of paramount importance. Now, you would not necessarily need to know about the geometry or physics of light, the mechanics of light, the phenomenon of light, what is it, anything about it, the mathematics, whatever, because all you are after are the photographs. Well, that's how I started out. But curiosity is a major driving force of a full-grown human being. And it's not just full-grown. We're curious out the gate. Kids are absolutely curious about pretty much everything. Now, another reason to know a lot more about astronomy than you may have been taught in school, for instance, or you've learned thus far, is because kids are going to ask you questions that kids have been asking since the beginning of time. For instance, what's at the edge? How far can I see? It's nice to have those answers, not just for yourself, but for the sake of those whom you would not want to turn away. You want to get them more interested in what you found to be ultimately satisfying because it's beautiful. Now, without going into philosophy, I accept that as the basic premise of science. It's not to get technology. Jets, rockets, lasers, they're fine. Computer chips, cell phones, they're fine. No objections at all. Is that the main purpose of science? Absolutely not. Absolutely not. Because we're humans and we are on some kind of mission. Now, as a group, forget it. We failed, and pretty soon the Earth will be destroyed. But that does not change anything. What we do in science is independent of the fate of the Earth. Has nothing to do with saving the puppies, has nothing to do with justice, has nothing to do with medicine, prolonging the human life or making the human condition better. We're not after any of those short-term goals. We want eternal answers. We need to have information to guide us beyond the gates of death. And if you're a mystic and you think you can achieve some kind of satori or moksha or transformation while you're right here on this planet in your body, goody for you and good luck to you. What we do here is, and I'm not speaking only for myself, and I'm kind of speaking as the voice of science here, what we're after are the actual answers to rational questions, any of which that we ask of the universe, we will get an answer. The universe will answer us. In other words, this is blueprinted. This is exactly what a full-grown man is supposed to do, and that's an identity. You're not any kind of a man until you do what I do. It's harsh. It's brutal when it's put into those terms. You might arouse emotions in you. Suppress your sicky little emotions. We are after the absolute answers for salvation of our goddamn souls, to put it nicely. And then we push all of that into the background. And now we deal with pure logic, just the facts. We're not interested in your opinion on levitation or how you're going to save the puppies. You go to the voting booth or you put on your army boots and you go out and do your thing. But here, we're not interested in your opinion. Nobody is interested in my opinion, least of all myself. But we are human, so I thought I'd bracket how it is that we remain human or are human as we do science. It's because we want the answers that will save our souls. Normally that's called religion, isn't it? Not here, it's not. There's no mention of God. Not because God doesn't exist. We don't even talk about God because it has no definition. It's nothing to do with religion in that mythical sense. Yeah, your God, you go into a church, everybody's idea of God is their own. And they don't share it. Or if they do, goody for them! They have a nice social club, but they're not getting any answers, and they're probably not saving their souls. We have no opinion on that. I do, because I was in the church for 30 years. I'll never go back in. What I've seen in science is, well, science is no different. Not today, but it never has been different. We make progress, but each human being has to make the same progress. If you start repeating what your professors say, you'll never learn anything. You won't learn anything until you're up against your own limit and you want to understand something and you can't, and nobody can seem to give you a satisfactory answer, like why do two magnets attract, or what's at the end of the universe. Any of your questions about reality, you're free to choose mysticism, you're free to choose religion. That's not what we do here. We're not interested in Bernardo Kastrup's Eastern mystic philosophy of we don't see anything for real. Yes, we do. And that can be proved. In that sense, I take Tim Maudlin's side, but I would not be caught dead on the same list as Tim Maudlin, because I know what he is. Because I saw him in concert with Bernardo Kastrup. And those two men can't stand each other. They were on the Kirchheim-Mungel show and prepared to talk about some of the deepest secrets of quantum mechanics. They got into the conversation for 2 minutes. They ended up calling each other stupid. And one of them turned tail and ran like a coward, and the other one just sat there like a dictator. Both of them, as far as I'm concerned, absolutely disgraced. Absolutely disgraced. If you can't even, with an arbiter, with a referee, you can't even talk about your differences, you're not a scientist. You're a human, yeah. That's not the kind of human we need in science. We need someone who's willing to talk about the facts and stick with the facts, not guess. No theory, no model. Theories and models are for people who need them. A real scientist hates them because they're guesses. Models have caused more destruction in the 20th century going right to today. There are models that are destroying the minds of youths right now. The model of natural selection, biological evolution, totally disproved. Who's going to change it? Nobody will. That theory will be taught as fact until this planet is a cinder. And as for quantum mechanics, well, Richard Feynman has already told us. You'll never understand it, says Richard Feynman. Well, I do, Richard. And now I'm going to help you understand it as well. But I want you to know what I'm doing, because it might be a match on what either you want to do or you never knew that you wanted to do until I told you that maybe this is what you want to do. Which is what? Understand light. I'm an astronomer. I'm a deep space astronomer. I'm a galactic astronomer. I want to study galaxies. But I have found out that in order to understand what I'm seeing, and in order to meet science such as it is head on, to understand what's being told to me about the universe, about galaxies, clusters of galaxies, the cosmic web, the cosmic microwave background radiation, and the so-called cosmological model, I need to understand those. And these men who've been working on these theories and models for, these many decades now, but not much more than 100 years, they have their reasons for their models and theories. That doesn't mean at all that they're right. It doesn't mean that they know what they're talking about in any way. Every single man has to take the same path as all the discoverers. Any stone that you skip in traipsing along that path, you're just believing. You might as well be in religion. You have a belief. Oh, do you believe in the Big Bang? Oh, well, then you're a believer. But does that make it true? There's a lot of people, in fact, most people that I've met throughout my course in life, when I propose something about the truth of something, we'll just say about the Big Bang, and I propose that perhaps there is a better theory than the one that comes up with a Big Bang, they say, well, it has to be true because the wise guys say it is. If you do that, you're sunk. Even if you're right, you're sunk. Because even if you think you know, when push comes to shove, you actually don't know. Only your direct perception will ever tell you anything about reality. And anything anyone says about reality that doesn't match what you know about reality, you're going to have to do something about that. That's what I had to do with a cosmological model. Because I was inundated. It's inundated with black hole, black hole, black hole, Big Bang, Big Bang, Big Bang, inflationary period, inflationary period. And all of these catchwords. Accretion disk. Have you heard of an accretion disk? If you haven't, and you get into astronomy, you will. What we want is not any theory of quantum mechanics. I'll tell you what I want. I want to know how light propagates through space and how it carries all the information that it does to our eyes and to our photographic plates. What is the physical origin of light? Why does it travel at the speed that it does? How does it travel? How does it get to our eyes or our photographic plate? How is it processed? What makes that happen? That's physics. But you see, I'm not into particle physics or subatomic physics or nuclear physics or quantum mechanics or quantum chromodynamics or quantum field theory or quantum gravity. I understand them now. I understand why these men say what they say. I know why they say these models are true. They're true for them, but they're not true. The only thing that's true is the universe. Nothing that men say is true. We have to use logic, though. That does not mean we need to rely on someone else's authority. If you do that, you're not doing science. You're just believing your authority. That may get you money. If it secures you a job and you're told to lie, I don't care if they tell you to tell the children that they're gay monkeys. Do it if you're making money, and then you'll answer to God. Not on my time, you won't. I'm not a judge. I'm not a judge of humans. But I have to be a judge of facts. I have to be a judge of theories, models, dogmas, propaganda. I have to be a judge of trends, pressures, the reason why men lie, the reason why men persist in lies, even when it's proved to their face that they're lying, they'll still lie and get PhDs and Nobel Prizes. It's not unheard of. So, that's not what you do and that's not what I do. If it is what you do, I'll talk you out of it, because I'm going to tell you what the universe says. I had to get that off my chest. I've learned that my listening audience is willing to put up with these kind of tirades because they know that once I'm done, I'm going to give them the gold. Now, so far, that's only about 50 people that I can count. But that's okay. I'm still young. So, we want to understand the proton, and let's summarize what we know about the proton and the electron, and today I'm going to tell you what the photon is. Not a guess, not a model, not a theory. What the photon actually is, so that you understand it and you want to understand more, because it matches what you know. Science has mysteries in it, but they're not supposed to remain mysteries. We're blueprinted to get the answers. We're not blueprinted to come up with theories. Okay? So, what's the proton? The proton is the only spatial particle. Any questions you might have, you just go back to the last lecture. So the proton is the only particle. It's a spatial particle. It's better to say it that way because the electron is another kind of particle. It's not a spatial particle. And we can now state very accurately, according to a well-known mechanical system that describes atomic physics, atomic mechanics, conceived before either the proton or the electron or indeed the atom had been discovered, but it's held its ground. It's Ruger Joseph Bošković's force curve, which he called attractive force, and the other one is repulsive force. He didn't specifically deal with this spherically in his diagrams because it's very hard to draw spherical diagrams. So it looks like it's linear. And in fact, the flight of the electron straight toward a proton is on a straight line. It's called a force line. And that's a straight line. For a particle such as an electron going toward a proton goes in a straight line. That's called a force line. And that is a valid linear construction. That is a straight line. Also, the flight of the photon from a star to your eye, I always have to add, or to a photographic plate. Since in galactic astronomy, it's never through the eyepiece. You can't see galaxies. Well, not nearly well enough. They just look like fuzzy things. But with photography, you can get a lot more light onto a plate, and then you look at the plate. You're seeing reality. You're seeing it well enough, the same way your brain would. It depends on the quality of the photograph. But we do need photography, so I do say that the flight of the photon from a distant galaxy, which would be from a distant star if it's a photon, that photon goes on a direct straight line into your eye. Or into the eyepiece, okay? Where it's finally captured on a photographic plate. Actually, in CCD capture these days. But it's all the same. It's getting an image of the photons that are coming. Now, it's hard to argue with a construction of light as consisting of photons. Newton thought so, and Einstein thought so. However, that's only half right. And we know that. It's called the quantum paradox. So yes, photons behave as particles. That's a dead straight line from the star to your eye. Now that's impossibly straight, and that should alert you to something about linearity. When you're talking about a photon, you're wrong. I'm just going to tell you. There's no such thing as a photon except at a infinitesimally discrete moment. And that's part of the measurement problem. So we're going to get to the photon today. The photon is a quantum of energy. Now you know that. It's a quantum of energy. That's why it can be called a photon. Because a particle and a quantum are the same thing when you use the word quantum the right way. Quantum is actually an adjective. So it's quantum energy. A particle of energy. There are two particles of energy. One is called the electron. That is a particle of energy. The photon is a particle of energy. How real are those things? Well, we know that they're not quite real. We can definitely say that. They're not really particles. The question then is, if they're not really particles, first of all, why do they act exactly like particles? And the second question is, why do they not act at all like particles? It's because either virtually or in reality, they're in two different states. and the photon has two different states, and the electron has two different states. That only leaves out the proton. Does the proton have two different states? It turns out it does. The proton has two states that are governed by a three-quark process, or a three-quark mechanism. It's hard to talk about quarks. They're classified as particles. They are certainly not particles. There's no way that a quark, first of all, they can't be isolated. In none of the cyclotron experiments, we now call them hadron colliders, there is no such thing as a quark. However, they exist mathematically. You can extend that to the other particles. However, that is a most fascinating field that we're not going to get into because we don't need to. Although we might. There's a footnote there. We might want to get into the Standard Model. I do want to get into it, but it's extremely complicated. Extremely complicated. That's why so few people understand it. But the model is promoted, and there's reasons for that. But when you're talking about particles, you need to begin the way you and I began in the last two lectures. And then everything begins to make sense. This is called the axiomatic basis. In this case, the correct axiomatic basis leads into insight so you can understand what's being said. So what is a proton? It's a spatial particle. Why do I say it has two states? Because the three-quark system that Gelman identified, and I believe he got a Nobel Prize for this, he identified one of the only pieces of information we have about the proton is that it can be shown mathematically to depend on a three-quark. It's actually a harmonic, and we'll be talking about that, if not today, then soon. But the proton can be thought of as a mechanism. And one reason protons are being crashed together to explode them to see what flies out is to try to find this mechanism that makes the proton what it is. And what is it? It's a quantum of space. Accept that for now. It's the particle of space. It's the space particle. And it manifests itself by a force field. And the force field that makes it impenetrable is centrifugal force. The electron proves that. So the proton exerts a centrifugal force, and it has a force field that goes out to a certain radius, not very far. It's measured in femtometers, the smallest useful unit in subatomic particle physics is the femtometer. Because a proton is approximately, you could say it's about 1 femtometer radius. About. It's very difficult to get the surface of a particle. But the proton is well known for its behavior. It creates a shell around it that's a spherical shell that the electron will not penetrate. Outside of that shell, electrons are attracted to the proton. They will go toward the proton because of centripetal force. And that's called the attractive force. In the integral scale of protons, that's called gravity. There is no difference between protonic centripetal force pulling in the electron and a body like a star has a gravitational field. They're identical fields for that reason. You know what causes gravity? It's mass. You know what the definition of mass is? Protons. And there's your connection. That's the unified field theory. We just got it. Not quite, because we want the mathematics that proves it. That has not been discovered. There has never been a theory that's united what's called electrodynamics, although that should be subclassed, but it is a branch of electrodynamics. So far, we found no relationship between electrodynamics and gravity. Yes, we did. I just told you the relationship. They're both centripetal force. And there's no difference. Because there's only one centripetal force. What is that? It's a pulling in of space. It's a contraction of space. Einstein taught us to say that. He said it that way. Everyone says it that way. Dr. Sabine Hossenfelder says it that way. Not only does Sabine Hossenfelder, in a very recent one of her broadcasts, not only does she say that the definition of gravity is that space is bent, but she goes further, and she's not alone in doing this. This is in a lot of textbooks, that gravity is not a force. Yes, it is a force. It's absolutely wrong to say that it's not a force, but you could make a case, and Sabina does, and a lot of PhDs do. They say that gravity is not a force because what's holding you up on the earth is the pressure of the atoms under your feet. They're holding you up so that you don't plummet into the center of the earth, but it's not a force that's pulling you in. Rather, it's the atoms that are holding you up. So, there's actually a way you can make that work. And let me tell you how she is right, although she's not right in saying that it's not a force, although she can make a case for that, and a lot of PhDs do, that gravity is not a force. It has to be a force because it has an effect on space. So why would anybody say that gravity is not a force? Because it doesn't have motion. There's no motion anywhere. If there's a star, we know that it has a gravitational field, but there's no way to know that by looking at it. The only way you know that a star has a gravitational field is if you can see something moving near it. And if it goes in a circle, or in fact an ellipse, as all the planets do around the sun, then you know, or you can eventually prove, as Kepler, Newton, and Einstein did, it's exerting a force. That planet is exerting a force in space. That's energy, but it's not called energy, and it should not be called energy. It should be called what it should be called, a force. But a force is conceived to depend on energy. And that's where Sabina gets confused. And it's a wonder she made it as far as she did. If she's willing to say, as many times as she did in her presentation, that gravity is not a force, after about the 6th time I got sick of hearing her say that. But she was trying to make a point that's actually very well taken. It's just that she didn't take that point. She's merely being ignorant and saying something that's not true. It can be that close between truth and just getting it ass backwards. If you don't understand what you're saying, so the proton is a particle because it creates a center, and that's the same force as gravity. And how can I say that if the proton has a centrifugal force field around it? How do we know that? Doesn't that sound crazy? Have you ever heard anyone say that a proton has a centrifugal force field around it? Nobody has ever said that. Oh, yes, somebody did. Ruger Boshkovich said that. That a particle, he didn't use the word centrifugal force, though. That's my discovery. That is the correct definition of centrifugal force. It's exhibited by the proton, the space particle. It creates a position in space. That's the definition of a particle. Is something that has a position in space, but you need to say more, because a planet has a position in space, right? Yeah. So what about at the smallest level? Is there anything that we can say that's the smallest thing in the universe that has a position? Yes, it's a proton. How do we know that? We know it because it has a force field around it that keeps it at its own center in space. How do we know that? Because when an electron gets close to the proton and it reaches that centrifugal force, it shows, the electron says, I just ran into a force that I can't get through. Well, that is called a centrifugal force. So the proton exhibits centrifugal force. That's throwing out. It's a pressure that goes out from a center, out from a center. I know this sounds like second grade stuff, but this is exactly the stuff that all the physicists are totally overlooking. They're overlooking the obvious. I'm not, but I've had help. I've had help from Einstein, from Planck, and from Bošković. So this is the result of those men's discoveries. I am a geometer. I'm a synthesizer. That doesn't mean you make synthetic nylon stuff. It means that you synthesize knowledge into understanding. So the proton is the only space particle. The reason it is a space particle is because it has a centrifugal shell that is impenetrable. It can't be broken by the electron. By the electron. Okay? So the electron proves that the proton is a space particle. Now, what does that make the electron? We covered that in the last lecture, and I hope you were impressed. But this is where it gets really, really good, is when you summarize so as to synthesize and re-examine what you may have caught a glimpse of before, but now I'm going to make sure you understand it. And if you don't understand what I'm saying, look at the last lecture. Don't forget, this is the most difficult problem that's ever faced the human mind in physics. I got the answer. So that's what I'm going to give you. The particle is a proton because it has a force field around it that's impenetrable to the electron. The electron has a force field that holds it together that's the opposite of the proton. The proton holds itself together in space to make itself a center by pushing out to a limit with a pressure. It's called a force field, right? Just like in Star Wars. It's a force field. And at that radius, the radius of the centrifugal force field that the electron proves exists, beyond that, it's a centripetal force that pulls the electron in. So the electron goes toward the proton. When it reaches the centripetal limit, that's a sphere. It's a spherical surface inside of which the electron cannot go. Why not? Because a force is stopping it. What's that called? Centrifugal force. For the exact reason that what's pulling it in until it gets to that radius, that's centripetal force. And Ruđer Bošković was the first man on Earth to ever say, completely overshadowing the work of Newton, who now fades into the woodwork. I'm being emphatic. If you know what Newton said, but you don't know what Bošković said, you don't know anything. So I'm going to share with you what Bošković discovered. This has to do with gravity, don't forget. That's the other way we know of the universe. It's not just light, it's gravity. And that's why there's the search for quantum gravity. It's to unify electrodynamics with gravity. What that is the effort to unify what we know about macroscale phenomena, including gravity, with microscale phenomena, which leads to the quantum paradox. In order to understand how everything works together, you have to understand the quantum paradox. Well, nobody ever has. Richard Feynman says nobody ever will. I say I do. And this is how you get at it. You first realize there is only one space particle that has a centrifugal force shell, beyond which its centripetal force. What Newton said was, there's only one force in the universe, centripetal force. These are the two spherical forces. I've already proved those are the only two forces in the universe. You can say there's linear force, not in spherical form. No. The universe is spherical, not linear. We see macroscale phenomena that look like they're linear. And some of them, is hard to deny, are not just macroscale, such as the flight of the photon. Yes, okay. So we're getting, and a force line. A force line of gravity is a straight line. It's just that the entire force is all those lines. It's a spherical phenomenon. So in the spherical world of the universe, beginning at the proton and the electron, going to the photon, and then planets, stars, galaxies, and the universe itself, spherical, 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 spherical. Nothing is linear. So what are the two forces in spherical space? The one that goes out from the center and the one that pulls in. That's what Ruđer Josif Bošković said. The particle that he saw in his mind, without any experimentation to back this up, his work has never been denied or overturned in any way. So he's right. Faraday said he was right. Bohr said he was right. Tesla said he was right. I say he's right. It's not just attractive force. The source of gravity is the proton. I've proved that, so you don't need to it doesn't make any difference if nobody else knows that. I do. I've proved it. There's no way, actually it's self-evident. It's just nobody has the mathematics for it yet. I'll show you why nobody has the mathematics for that. It's not because the universe is at fault and, we just will never understand it. It's because your goddamn mathematics is stupid. You're not using the right mathematical system. That's heresy. Good. Because if it is heresy, then I'm going to heaven and they're going to hell. Thank God it's not religion. Yes, it is. This is rational logic. You either get it right or you get it wrong. And if you're trying to teach others and you've got it wrong, you're a liar and a deceiver. And there's no way around that. You may say, science is supposed to be safe. We're safe from all these religious nuts. Yeah, until you get to the top. Until you get to the edge. Until you get serious. Until you grow up. And you have to have the answer. And you're sick of being lied to. And you don't like models. And you don't like calculus. And you don't like liars. Okay? This is a fight to the death for the truth. That's the way I treat it, since I have the answer. So, coming up on an hour, I suppose I'll publish this, but I think I'll make this a link. In the next lecture, we'll get into the good stuff. So, thank you for tuning in, and if you've tuned in for either the last 2 lectures or the last 3, this one being the 3rd, thank you. It means a lot to me to know that there are listeners. I'm not just doing this to teach myself anymore, although that is how I began, was to hear myself, because I was on a discovery vector. Well, that discovery vector has turned into the greatest sequence of discoveries in the history of science. So when I appear before God, I'm going to be happy. Will you? I could say that I don't care. I could say that that's my main concern. Guess. All right, it's not every man for himself in science. We're all in this together. I do need you, but not to the same degree that you need me. This is Anagalactic. Don't forget to keep looking up. We'll be right back. If I can find the stop recording. Oh, and this is the 3rd day of February,
This is
a Saturday. Bring you
right
another
back.
science presentation. There's only one space particle. The reason we know that is because it makes a centrifugal force field around it. Centrifugal force. That's force going out from the center of a sphere. That's what the proton is. It's a centrifugal force field with a most interesting characteristic at the surface of the force field where it's pushing out. How do we know it's pushing out? Because the electron can't get in. And the electron demonstrates that it cannot get in. When it approaches the proton to that radius, it goes at a 90-degree spherical angle and envelops the proton in a standing wave form. All of that is known. None of this is new. None of this is breaching anybody's theoretical model. That is known. What is not known is the word centrifugal. That has never been thrown into the mix. I'm throwing it into the mix because it's the right way to say it. So there are 2 forces in spherical space. This would be the universe. This is, remember, we're talking at the scale of the smallest things. The proton is the smallest thing in space, okay? And the reason we know that is because it makes a force field around it that's an outward pressure. That's called centrifugal force. On the other side of that radius, it's centripetal force. It's pulling in, and it's bending space. It's bending space down to its centrifugal shell. So, that is the center of space. But that's only one part of the story. We found the space particle. It's defined as a balance between centrifugal central force and centripetal exterior force. It's centripetal going all the way into the shell, and the 2 pressures meet there. From the center going out, the proton generates a centrifugal force field. On the other side of it, it's the opposite. It pulls in. The electron is not a spatial particle. The reason we know that is the exact inverse of a proton. Instead of having a centrifugal force core, the electron has a centripetal force core. It holds itself together. Well, what's it holding together? A centrifugal force. That's called energy. It's also called angular momentum. It also manifests something called periodicity, and it has a most interesting effect on us as humans. It manifests time. The proton does not do any of that. There's no motion. There's no angular momentum that we've been able to measure. There's no periodicity, and there's no sense of time. The proton is a space particle, beginning at the center, which is the 3-quark mechanism, which is a harmonic. We'll be getting back to that. The 3-quark harmonic generates 2 forces. The innermost force is centrifugal. On the other side of that radius, it's centripetal. So it's the centrifugal, centripetal space quantum. It defines space, and it has no knowledge of time, no knowledge of motion, no knowledge of angular momentum, no knowledge of periodicity, which is at the basis of time. None of those things. It's pure space. It's everything we know about space. The proton and space are the same thing. Accept that for now. The electron is not a centrifugal, centripetal space particle. The electron is a centripetal, centrifugal energy quantum. The electron is the angular momentum particle, the motion particle, the time particle, the periodicity particle, the motion particle, the energy particle. That's not space. None of those terms are spatial. They all have to do with what we think of as time. We're going to think of that better. Time is the wrong word. You can make it the right word. Albert did. We're going to find out what time is. But it's all four of those things. It's motion, periodicity, angular momentum, and time is a derivative concept. Okay, that's what we're getting to. So those are the two fundamental particles. So it does have to do with chirality, but that's not going to be in this lecture. So now we have 2 out of the 3 standard particles. The third one is the photon. Is the photon a particle? The word itself, okay? If you say photon, you're saying particle, yes. Is it a particle? Because Christian Huygens was correct. It is a wave. Light is a wave. Well, can it be both? No. No, it can't be both. That's not a paradox. That's the nature of physical reality. Either light is particulate, it's made of particles, or it's continuous. It's either made of photons or it's a wave. And it can never be both. And it has to be one or the other. It can't be both. There are 2 kinds of particle. But now you have to be extraordinarily precise in what you mean by particle. Only energy produces motion. There's no such thing as a static sphere. The electron is the manifestation of centrifugal force. The proton is the manifestation of centripetal force. Both the electron and the proton have both forces. They manifest both forces. But they manifest those 2 forces in reciprocal relationship. The proton manifests centrifugal force out to that radius, and then it's centripetal from then on. The electron manifests exactly the opposite. Centripetal force out to the limit of its radius, and then centrifugal force from then on. But the centripetal force is holding it in. How do we know that? Because of the behavior of light. But that's the centripetal force of energy, okay? Which is not space. It's the centripetal force of energy. That is the centripetal force of time. These are virtually equivalent. I'll show you they're not really quite equivalent. You could also say it's the centripetal force of angular momentum. You could also say it's the centripetal force of periodicity, none of which are spatial concepts. It's the inverse in the proton. The proton has the same spherical shell. They both have shells. But the relationship of what's on the outside of the shell and what's on the inside of the shell is inverted between the proton and the electron. There's more to be said, though, because they're not operating in the same space. And space here is either the time space or the spatial space. When the proton manifests its presence as the quantum of space, that's exactly what it is. It's the quantum of space. When it does that, its centrifugal force, we don't know what causes that, except Gelman figured out a mathematical construct that gives us a lead. There's a harmonic that drives the protonic centrifugal force. So it generates a centrifugal shell, a pressure shell. It's a force field. That is called a force field. The electron has exactly the opposite of that. It has some kind of force inversion field where at the surface of the electron is pure motion, it's pure time, it's pure energy, it's pure angular momentum. It's definitely not space. It's the other thing that space is not. And that's the surface of the electron. But then you have to ask two questions. Why doesn't it just disperse if it's energy? Spinning is trying to go out. Yes, that's centrifugal force. Why doesn't it go out? It's because it's being held in by some mysterious centripetal force. And that's correct to say it that way. We don't know what that is. Well, we're getting there. But you have to take this one step at a time. It's almost tautological, so it's best just to say the obvious. It's a sphere that's rotating, and so since it's a sphere that's rotating, that generates centrifugal force. If you don't believe me, get on a merry-go-round and have someone spin you until you fly off of it. Okay, yeah. That is centrifugal force. It's due to angular momentum. So angular momentum and centrifugal force are equivalent. Angular momentum is the only proper motion in the universe. It is the definition of motion. The electron is a manifestation of energy. That is well known. I'm saying that that is angular momentum and therefore it's centrifugal force. That is correct. That's the definition of energy. It's centrifugal force. Remember the scale. We're talking about the building blocks. This is not macroscale. This is the way things actually happen at the so-called quantum level. We're going to break all of the mysteries open, so nothing is going to be mysterious anymore. Not even entanglement. And we'll get to that. That's the hardest one. That's the one that Einstein did not like. Because it suggests transluminal information transfer. Now we know that that's not actually what it is. And whenever you see these Bob and Alice experiments, those are all horseshit. And they don't cover the true nature of entanglement or superposition. Bob and Alice experiments are propaganda. They're pure propaganda. There's no Bob and Alice exchanging anything that means anything. It doesn't prove anything, any of these Bob and Alice experiments. They're nonsense. Pure nonsense. And I'm going to help you see that. The only way you can see that is if you know the right answer. So let's keep going. The electron is centrifugal force. The proton is centripetal force. At the core, each one is balanced with its opposite. So each particle exhibits both forces in perfect balance. But the space particle manifests a perfect space orientation. We're talking about time-space now, right? Yeah. Time is very, very misleading term. And you can use any one of the other three terms. Either think of it as motion, angular momentum, or periodicity, but don't think of it as time. Time is a derivative. You know how we know that? Because it's linear. And I'll show that to you in a second. This has to do with the flight of the photon, which is what we're getting to. What is a photon? Okay, there are two places in its lifespan or its life cycle where it's a particle. It's a particle for an infinitesimal amount of time and space. And in fact, that time and space don't actually exist. So it's never a particle. But unfortunately, the only way we can measure light at all is when we see it as if it were a particle. And that shows up in the photoelectric effect, where it's inescapable that light behaves as a quantum packet. That is an illusion. And no, there is no such thing as a particle of light. and Newton was wrong. Light does not travel in particle form. That's actually ridiculous. It's actually absurd. It's actually contrary to everything we know about light except at the moment of measurement. That's the quantum paradox, and that's Schrödinger's cat problem, is that when you're not looking at it, it's real. But when you look at it, it's not real. Energy is never a particle. There's only one particle in the whole universe. It's a proton. That does not include the neutron. That's not even on the list. It's a proton. That does not include the electron. That's not on the list. Only the proton is a particle. You have to get this through your head. Because it's a space particle. That's redundant. The only particle that can be a particle is a particle in space. Well, there's only one of those. As for the neutron, that's the altered state of the proton when it no longer has the same valence of its harmonic. All of this can be understood. I'm merely telling you point blank what I know, but all of this has been proved. There's only one particle, and those 36 and a half, whatever they think, including the Higgs, those are not particles. Although you could make a case that all 36 of them are particles. I do, because you got to give these guys some credit for having half a brain in their head. They've discovered all these things not in vain. These things actually leave trails in the bubble chamber. But to call them particles is the sign of a jackass. These idiots keep calling them particles. You know why? They don't have a brain in their head to figure out that they have another choice. To call these things what they really are. And they're certainly not particles. And all this stuff about gluons and virtual photons, these are mathematical constructs in order to support their particle theory. It's a purely mathematical nightmare. They can make sense out of it. They say, well, I say, no, you can't, and no, you haven't. And I'm right. And they're all wrong. And those are not particles, because not even the electron is a particle. And the photon is the least particle thing of all the so-called particles. There's only one particle, because there's only one presence in space. The electron is not spatial. Nothing about the electron is spatial except for locality. But inside that locality, it's a wave. And a wave cannot be a particle. And so it's not a particle. And that thing you're firing from a gun that you say is a particle, no, it's not. It's a wave. It's a wave that has a centripetal force that binds it. Now, if you say that makes it a particle, I'm going to say you don't know left from right. The problem with a paradox is that you can say it that way, but if you do, you won't make progress. You actually have to say it the right way when it looks like there's two equally right ways. No, they can't be equally right if they contradict each other. You have to figure out which one is right. Nobody's been able to do that. And so Feynman felt like he just pulled his 2 6-shooters out and started shooting into the sky. No one's going to figure this out. Bang, bang, bang. Yeah! As he downed some scotch and went to Esalen and balled some chicks and smoked his cigarettes and dropped bombs on Japan. That's Richard Feynman. I respect everybody for what they do. I am single-minded, though. I'm sorry. I have to apologize. I'll do anything to get the truth. But once I have it, it's my duty. I am blueprinted. I'm under orders. If I get it, I have to share it. That's what I'm doing. Does it look like I enjoy it? Yeah, I love it. Everyone's gonna hate me. Well, I'm just trying to get it out in the open now. Now I've given you a reason to hate me. My face turns red. I guzzle beer. Yeah, this is my medicine water. Let's just take a good look at this. This is where I live. I actually live in Old Chico. Although, where Sierra Nevada comes in, we're quite a ways from the Sierra Nevada. But I'm never far from this. Because I'm 70 years old. I know I don't look it. That's because I've... Ponce de Leon was looking for the fountain of youth. Oh, he just barely missed. Yeah, you can tell I'm white. You know what white means? Pink. It means you're pink. That's where Adam comes from, by the way. That means ruddy. So the first humans were white. Contrary to what you're taught in school, which is that the first humans were gorillas in Africa. Goddamn racist fucking theory. Actually, the truth is it's neither white nor black. The first humans were brown. But that's only after the flood. Alright, so what's the photon? I think that's enough. 40 minutes. We'll be back. This isn't the first one of these. I told you I'm 70. Dying a campfire smoke in my lungs. Oh, God. No, we'll be back. Don't worry. Oh, by the way, there's another lecture that precedes this, which was an actual rant. I know. You must think, I gotta see that just to see. He gets even more obnoxious than he is now. Oh, yeah. Oh, yeah, I absolutely can. Well, we'll be back. Just make sure you tune in. I will. I'll be here. I'm not supposed to laugh. Doctor's orders. It's too late. I got the secrets of the universe. Don't forget to keep looking up when the clouds part at night. We'll be right back. I swear. I mean, I can't because I might die. I'll be back, okay?